thank you so much. It's great to be here and to see so many familiar faces. So in this next section, we're going to take kind of a deep dive and look at some of the latest from Antarctica, or as it's often also called, the eternal ice, and take a look at the dynamics there and whether or not it actually is the eternal ice. Excuse me. Yeah, this year has, of course, been special in so many ways. It was actually termed the super year in advance by the UN because it's 5 years after the Paris Agreement. It's also 5 years into the Sustainable Development Goals agenda. And it kind of turned from a super year into an extreme year in many aspects, Corona just being one of them. And what's often overlooked is that 2020 was actually also an extreme year in the polar regions, where we had hit temperature records from the Arctic to Antarctica, with plus 38 degrees for the first time ever being recorded north of the Arctic Circle. And that's 18 degrees warmer than the average maximum daily temperature in June, which is when this temperature record was recorded. And plus 18 degrees in Antarctica, which is also the highest temperature ever recorded in Antarctica and at the Antarctic Peninsula, and which was followed by widespread melting on the nearby glaciers. It's also a special point in time when we kind of take a longer time frame, because we're actually at a very, kind of special point in time, looking at this temperature evolution since the last glacial maximum here. So what we see here is the rise in global mean temperature from the last glacial maximum about 20,000 years ago through the Holocene to today. And there are two features that are really striking about this graph. First of all, what we see is that the Holocene was a really stable climate, at least in terms of the global mean temperature. And the second thing that we see is that the difference between an ice age and an interglacial as we have today is roughly 3 to 4 degrees of global mean temperature difference. And what we're facing today is actually the same or even larger changes in global mean temperature, but in a much, much shorter time scale in the future. So I think it's really fair to say that humans have become a geological force, and that we have truly entered the Anthropocene. And of course, humans have also been influenced a lot by the glacial cycles in the ice sheets on Earth, and vice versa, as we will see in a minute. So why are we so interested in the ice sheets on Earth? They can often seem kind of far away. One of the reasons we're interested in Greenland and Antarctica for sure is their sea level potential. This means if we were to take the entire ice volume of the Greenland ice sheet, and if it melted down completely and we distributed that meltwater across the global ocean, then global sea level would rise by roughly 7 meters. So this is truly a sea level giant. And for West Antarctica, it's another 5 meters. And for East Antarctica, the sea level potential is even the tenfold, so more than 50 meters worth of sea level rise stored in the East Antarctic ice sheet. Where we're at right now, currently the ice sheets are actually on track with the highest climate scenario, the RCP 8.5 scenario from the IPCC report. You can see here the observations marked in gray, and then the lower, mid, and upper ranges of the projections. So we're really tracking this higher curve here. And that means that the ice sheets are actually even more vulnerable than expected before. How does this ice loss come about? Well, generally we have, of course, a balance between snowfall that falls on top of the ice sheet and shelves, the floating extension of the ice sheet, and which is then lost through different processes, including melting at its surface, but also calving of icebergs at the margins, as well as subshelf melting, which plays a particularly important role for Antarctica. And what makes it so complicated to track and also model the development of the ice sheets is that we have several positive feedbacks in the climate cryosphere system that we need to consider. Some of these you know for sure. There's the ice albedo feedback. There's also the melt elevation feedback that we're all familiar with, actually from mountain hiking. So if you hike from the peak of a mountain to the valley, then of course the temperature around you increases, it warms, and the same is true for the ice sheets. And that means if you cross a critical threshold in the surface elevation, then the temperature at the ice sheet surface will be higher, it will warm, so that leads to more melting, and that in turn can lower the surface elevation once more, and so on and so on, so that you have a self-reinforcing feedback there. And there are two other major instabilities or positive feedback mechanisms that are particularly important for Antarctica, and those are the marine ice sheet and the marine ice cliff instability. And there are many other positive and also negative feedbacks that play an important role here in this interaction between the ice sheets and the climate system. As I said, in Antarctica, the ice shelves play an especially important role. In Antarctica, the mass loss has tripled over the past years, and there was especially high mass loss in the Amundsen and Bellingshausen sea regions here in West Antarctica. And the reason for this is very likely has to do with the warmer ocean temperatures that are around the ice shelves here in the West Antarctic ice sheet compared to many of the ice shelves in East Antarctica. There's roughly a 2-degree temperature difference between some of these regions. So Antarctica, especially West Antarctica, has lost mass, and one of the key drivers is the ice-ocean interaction, which has led to enhanced subshelf melting, so melting at the undersides of the ice shelves, and therefore to a decrease in the so-called ice shelf buttressing. So that's the backstress at the grounding line, which actually hinders outflow from the interior of the ice sheet into the ocean. So this means that with increased subshelf melting, there's also a great potential for more and accelerated ice flow from the interior into the ocean, and therefore sea level rise. So the question is, how does this impact the ice sheet dynamics overall, and also the stability of the Antarctic ice sheet? In this one region in particular, in the Amundsen region in West Antarctica, where we're now taking kind of a dive into, observations have shown, first of all, that the ice velocities have really increased over the past decades. Everything you see in red here, those are higher velocities. But not only was there an acceleration of the ice flow, but also the glaciers have kind of retreated into the deeper valleys. Everything that you see in brown here, this is where there's been a decrease in the elevation. And with this comes the potential for an instability mechanism here in the West Antarctic ice sheet. This is the so-called marine ice sheet instability. Basically, you need two conditions to hold for a marine ice sheet instability to potentially take place. And first of all, as the name says, you need to have a marine ice sheet, so one that's grounded below sea level, as sketched here. And secondly, the ice sheet needs to, or the grounding line needs to rest on a retrograde sloping bed, as indicated here. And if these two conditions hold, then in a 2D case, you can even mathematically prove that there is an instability until you again reach a stable grounding line position. So this is basically a positive feedback between the grounding line retreat and the flux across the grounding line, which takes place here and which leads to this enhanced ice flow into the ocean. Now, of course, in the real world, this is much more complicated. As I said, in 2D, one can basically mathematically prove and show why this leads to an instability. But in the real world, we have the ice shelves which are buttressing the ice sheet, and that also means that there can be some stabilization due to the ice shelf buttressing if it's strong enough. But the marine ice sheet instability might be potentially underway in the Amundsen basin, which holds enough ice to raise global sea level by roughly 1 meter. And what this means is that this, what was before kind of a theoretical notion of potential tipping points in Antarctica might have become reality here in the Amundsen basin. So what we were interested in is, are there further tipping points in Antarctica? And what we wanted to do is a stability check on the Antarctic ice sheet to assess the risk of long-term sea level rise. So what you will see next, those are not projections, but rather we've very slowly increased the global mean temperature as forcing, and then looked at the response from the Antarctic ice sheet in the hysteresis analysis. So this is very typical to very slowly increase the forcing. So you're kind of in a quasi-equilibrium state to then assess the hysteresis. And what we see now is an animation while we're increasing the global mean temperatures. And we find actually a sequence of tipping points here. Around 2 degrees, the West Antarctic ice sheet collapses. And this is mainly due to this marine ice sheet instability. And then also other parts of East Antarctica become unstable, starting with the Wilkes Basin here in East Antarctica. There's a second major threshold around 6 to 9 degrees, where then surface processes become more dominant. So there's also surface melting, and eventually the melt elevation feedback leads to a strong decline of the East Antarctic ice sheet, and around 10 degrees Antarctica can actually become ice-free. So we have this sequence of tipping points, which also goes along with these different processes. So really driven by interactions with the ocean for West Antarctica, and more dominated by surface processes in East Antarctica as the temperatures increase. We also checked whether these changes are reversible or not. And we found a strong hysteresis for the Antarctic ice sheet. So what you see here is at the upper branch, this is the retreat. You basically start at the present day or pre-industrial ice volume, and then increase the temperatures in this quasi-equilibrium manner. And we find these 2 major thresholds until Antarctica eventually becomes ice-free. And then we reverse the forcing, so there's a cooling, and we find that there are these major differences between the retreat and the regrowth path of, and in places it could be more than 20 meters worth of sea level differences. The currently observed ice sheet configuration is actually not regained even when the temperatures are reversed to their present day levels, but rather it takes another at least 1 degree to 3 degrees to actually grow back the initial ice volume. And then of course, the configuration is still different in terms of where the ice is actually located. Here's just another zoom into this retreat and regrowth path. So what we see here are the equilibrium states at 2 degrees of global warming and at 4 degrees of global warming, and then the same for the regrowth path. And you can see that, for instance, for the 2 degrees, the Wilkes Basin here in East Antarctica does not fully grow back. Yeah, I think this clearly shows that the ice sheets and actually other parts of the cryosphere are among the most vulnerable components of the Earth system. And now coming back to our general temperature evolution since the last glacial maximum, and looking at this in comparison to this temperature evolution, one thing becomes strikingly clear, and that is that the West Antarctic ice sheet and Greenland are among those tipping elements which are already at risk of transgressing a critical temperature threshold within the Paris range of 1.5 to 2 degrees of warming. One thing that we're particularly interested in now is understanding better if there could be any tipping cascades or domino effects in the Earth system. These are some preliminary results from a more conceptual model where we were interested in understanding the role of the ice sheets as well as the AMOC and the Amazon rainforest. And one very interesting finding is that in many cases, when we look at tipping cascades or domino effects, the ice sheets actually play the role of initiators of these tipping cascades, while the ocean circulation is rather moderating these effects and sort of distributing them globally. If there's one thing I would like you to take away from this, it is that ice matters. And here are 3 reasons why. First of all, we all know this, they act as an early warning system of what's going on in the climate system. And of course, they're also very valuable climate archives and tell us a lot about the history of the Earth system. Secondly, as we've seen, they're a major contribution to current and especially also future sea level rise. They hold the largest sea level potential. And lastly, they belong to really the most vulnerable parts of the Earth system in the sense of their tipping potential. Thank you very much. I'm looking forward to your questions.